Now let's look at this really fun question on the practice exam, problem 4. So it's short, but I've given a long hint. It says, show that of all the isosceles triangles with a given perimeter, the one with the greatest area is equilateral. Okay, so let's remember from 7th grade geometry what these terms mean. So isosceles means two sides are the same, right? So this means that it looks like this, A, and then this could be anything, okay? Alright, and what does equilateral mean? Equilateral means that actually all three sides are the same. So we have A. So maybe I should label these. So this is isosceles, and this is equilateral. Alright, so this is an optimization problem. And remember how these usually go. You have two variables, and then you use a constraint equation to get it down to just one, and then you just find the maximum of some function. Okay, so the constraint here, what constrains us, that's going to be the constraint. So let me change it to the constraint. Constraint is the perimeter, right? So the triangle is going to have a certain perimeter, and so it's an isosceles triangle. So what is the perimeter going to be? It's going to be A plus A, I almost wrote B, but let's say A plus C is going to be the perimeter. Okay, so I'm just using this little lowercase p is just going to be a constant that stands for the perimeter. It's just some number. That's a costant. Let me change it to a constant. Okay, so little p is just some constant that stands for the perimeter, and of course any sane person would rewrite this as 2a plus c equals p. Okay, and you know this is the picture that I have in mind here. I have an isosceles triangle. Two sides I'm calling A, and the other side I'm calling C. So those are the lengths. Alright, so here's my constraint equation. You can see that there are two unknowns. P is a constant. A and C are unknowns. And the constraint is going to let me write one thing in terms of the other. Alright, and now let's think about what we want to maximize. Okay, so remember the thing that we actually want to maximize is what we call the objective function. Okay, and that is definitely the area. Okay, so we want to look at the isosceles triangle with perimeter P and then maximize the area. Okay, but there are lots of ways to express the area of a triangle, right? We could do 1/2 base times height, or there's something also that involves the sine function. But I picked this awesome thing kind of just because I wanted to use it, but also because it's really practical for this situation. It turns out that there's a formula for finding the area of a triangle just from its sides. Okay, so this is called Heron's formula. So Heron's formula, sometimes according to Wikipedia called Hero's formula, is a way of finding the area of a triangle just from its sides. And that's not only fun, but it's actually convenient for us, because this way we don't have to compute the height, which we don't know, and we don't have to know anything about the angles. So we can just use the data that we're given. So this is the most convenient expression of the area for us to use. And you probably know what these ABCs are, but let me just show you. So in the formula, this is just A, B, C are just the three sides of the triangle. Okay. And alright, so this is the formula that we're going to use. It's going to be especially great for us because since we're using an equilateral triangle, we have A equals B. And so what is that going to do? That means these two terms in the middle, where we have negative A plus B and this one where we have A minus B, those are both going to just reduce down to, it's going to be C, right? Because A minus B is going to be 0 since they're the same. So maybe I should go ahead and let's write that out, okay? So the formula, the objective function, the thing that we're going to maximize, right now we're going to write it in terms of two unknowns, but then later we're going to use the objective function to eliminate a variable. Okay, alright, so what is it? It's going to be, when I write it I'm going to keep in mind that A is equal to B, okay? So it's going to look like 2A plus C for this first thing, and then it's going to be C squared in the middle because the A's and the B's are going to cancel, and then at the end it's going to be 2A minus C. Okay, and it's all going to be over 16. Alright, so this is going to be our objective function. And like I said, right now it has two unknowns, A and C, but we have here our constraint equation, which lets us eliminate a variable. Okay, and so choose the one you want to eliminate. I'm going to eliminate C. Okay, so I'm going to use the constraint equation here, and I'm going to use the fact that C equals P minus 2A. Okay, so since that's true, everywhere I see C in the objective function, I can just replace it with P minus 2A. Okay, alright, so let me go ahead and do that. So now let's write A is equal to the square root of 2A plus P minus 2A. Aha, it's going to be a very nice cancellation. Here I have P minus 2A squared, and now it is 2A minus P plus 2A, because it's quantity minus. And this is all over, for some reason, 16. Okay, and 16 is still under the square root. Now I have it down to one variable, which is excellent, and let me just smarten it up here a little bit. Okay, so here I have 2A canceling with 2A, and I can combine these two, so I should do that. So let's see what happens after I do that. Alright, so now I just have P for this first thing times P minus 2A squared, and then for this last thing it's going to be 4A minus P, and this is all over 16. Okay, alright, so keep in mind that now A is the unknown, and the perimeter little p is just some constant like 5 or something. Okay, so I want to maximize A. Notice that two things are true. Okay, so A is the area, it's a positive quantity, and another thing is that it's much easier to work with A squared. Okay, so what I'm going to do is I'm going to find the A that maximizes A squared. Maximizing A squared, because A squared gets rid of that dumb radical and it's much simpler. Okay, so let's work with A squared, and so that is P times P minus 2A times 4A minus P all over this irritating 16, which I could also get rid of, but I think that might be confusing, so I'll just leave it there. Alright, so now this is what I want to maximize, this function on the right side of the equal sign. So what I'm going to do is, first I'm going to take its derivative with respect to A. So remember, good old Leibniz notation. So I'll just take the derivative with respect to A, and I'm going to set that equal to 0 later. Okay, so I take, isn't there something squared here? Yes, this is squared, sorry. So now I take the derivative, so that gives me P times 2 times p minus 2a, and then a negative 2 pops out from that first part by the chain rule. Okay, and then I have to use the product rule, minus p, okay, plus alright, and this p, I guess, is gonna come along for the ride, and now p minus 2a just sits there, and now I take the derivative of this last part, which is 4. Okay, and this is all over 16. Okay, and now we're going to be able to massively clean this up. Okay, so let's get started doing that. Oh my gosh, why is it erasing relevant things and not this ugly little red slash? Here is the 16 back again, and I hope it didn't erase anything important. I don't think so. So let's clean it up. So I've got p. Alright, so look, here's 2 and negative 2. I'm going to call that negative 4. And I've got p minus 2a. And then this part, which is 4a minus p. Okay, and plus 4 here, 4p, and a p minus 2a squared. Okay, so I have some things in common to everything. So what I have in common to everything is, maybe I should write it here in blue. So what's common, I'll write it in light blue so you can't see it, is to all these terms is 4p times p minus 2, right? I can factor that out. P minus 2a, okay? So I'll factor that out, factor it out. So what happens when I do that? So I get 4p times p minus 2a, and now after the factoring I get minus 4a plus p for that part, and what's left over here is much less, is plus p minus 2a. Okay, alright. It's getting nicer. Over 16. And I'm going to have to give you some more workspace than I did, huh? Okay, so let's keep going. So the 4 and the 16 cancel and just make a fourth. Maybe I can even write it right here. This is going to be 1/4 and p minus 2a. No, I'm just kidding myself. I'm kidding myself. Alright, so with the 4 and the 16 canceled, I'm going to have 1/4 times p minus 2a. And what happens inside these other parentheses, I'm going to get minus 6a plus 2p. Now this is the derivative, and what I have to do is set this equal to 0, and I have to solve it. Okay, alright, so two pieces here. I have to think about what's going to make this piece 0, and what's going to make this piece 0. Okay, so the thing that makes this piece 0 is if a is equal to p over 2. So that's pretty clear. Alright, that'll make that part 0. And what about this thing? This will be if a is equal to 1/3 p, so p over 3.